Hi all. We're going to be doing A-Level Paper 3 AQA today. So we can start now. Okay. This is the 2019 Paper 3 A-Level Chem AQA paper. The first question here is asking you, sodium thiosulfate reacts with dilute hydrochloric acid as shown. Give the simplest ionic equation for this reaction. So when it comes to ionic equations, you either know immediately what to do, or you can do the step-by-step method for it. I know it's quite a bit of work for 1 mark, but it's foolproof and it helps you to understand how it works. So I'm going to put it at the bottom here. Let's do the ionic equation for this. So the rules for ionic equations. No, this is A-Level Chemistry, Paper 3. So the rules, but it works as well for GCSE for the rules of ionic equation. Yes, it's A-Level. So rules for ionic equation. So for ionic equation, you need to have ionic aqueous compound, or you can have an acid. Acids are always aqueous. So you need to check here for each of them if they're aqueous, if they're ionic, if they're an acid. The first one here is definitely yes, ionic. It's got sodium, metal, and thiosulfate, which is non-metal. So you have ionic, yes, it's aqueous, so it does split up. For HCl, yes, it's acid, so it will split up. Sodium chloride is once again ionic and aqueous, so it will split up. This one's a gas, so it's not ionic. It is not aqueous. It is not acid. Same with the rest here. Not ionic, not aqueous, not acid. Only these two can split. So let's split them up. For the Na2S2O3, it will split up to form sodium ions and thiosulfate ions. Sodium ions is in group 1, so that's Na+, but there's 2 of them, so it's 2 Na+, and it's aqueous, plus your thiosulfate, which has a charge of 2-, so it's S2O3 2-, aqueous. Then you have your HCl, which will split to form hydrogen and chloride. That's the definition of an acid. You have 2 of them as well, plus 2Cl-, aqueous. And then the NaCl is 2Na+, 2Cl-, aqueous. And the rest of them, they don't split up. They can't split. So only the aqueous can split if it's ionic or an acid. How do you know it has a charge of 2-, and why isn't it split into S and then O as opposed to S2O3? Okay, so this whole thing here is called a thiosulfate. S2O3 is thiosulfate. Thank you, Bella, for the award. So this is called a thiosulfate. And I'll show you how you can know the charge without actually memorizing it beforehand. So we know that we have sodium 2, S2O3. In ionic compounds, we always split them up into the metal and the non-metal. So that's why we don't split up this into S and then O separately, because these two are considered as one non-metal. It's a molecule, so you can keep them together. To know the charge is by looking at the number of the sodium. Sodium has a charge of +1. So if it has a 2 here, that means this 2 must have come from the opposite, which is the S2O3 minus. And that's where you have the S2O3, 2 minus. That's how we know the charge. Obviously, you can also memorize it, but aside from that, you can do it that way. Would that be the same as the simplest ionic equation? Yes, so we're trying to make the simplest ionic equation here. So after we split them all up, all of the ionic ones, keep all of the normal ones. So the SO2, gas, S, solid, and water, liquid. The next step is to cross out the ones that are exactly the same. So you can see here, what do we have? So sodium, we have 2Na+, 2Na+. They're the same on both sides, cross it out. Then we also have Cl-. That's exactly the same, cross it out. Remember, when it's exactly the same, you literally have to make it exactly the same. Like same charge, same symbol, same state symbol, all of them has to be the same. So we're left with S2O3 2- aqueous plus 2H plus aqueous, giving you SO2 gas, solid, no, not solid, sulfur solid, and water as a liquid. And there you go. That's your simplest ionic equation for that reaction. That's how you do it. I know it's a little bit long, but once you get a hang of it, it's really simple afterwards. So we have here S2O3 2- AQ, 2H plus AQ, SO2 gas, S solid, H2O liquid. After the splitting, yes, so I just leave the ones that don't split, I just leave them behind. Like, you can just keep it at the end there as it is, and then just rewrite them again. Because they don't split, you don't need to do anything to them. So you can just keep it as is, basically. So that's the first one. Again, that's only for 1 marks. So what are the two that don't split? The ones that don't split are the ones that are gaseous, solids, and liquids. And how can you do all that for 1 mark? So yeah, basically, this is for 1 mark only. But if you, sorry, I lost my track of mind. So yes, this is only for 1 mark. You can do it like this, or you can kind of see what's going to happen already. You can see here sodium, sodium, chlorine, chlorine. So you can kind of see what's going to happen here. But this just helps you to see what charges will form, basically. Okay, now the next one. The gas SO2 is a pollutant. State the property of SO2, so that's sulfur dioxide, that causes pollution when it enters rivers. Give an equation to show the reaction of SO2 with water. Okay, so the main thing about SO2, or basically any covalent bonded compounds, so covalently bonded simple molecules, they are acidic in nature. Which means if you have covalently bonded simple molecules and they're acidic in nature, then the property must be that they are acidic. This causes pollution when it enters rivers because it's acidic. We don't want acids in our rivers, do we? So that's one of the things that you can put in there. You can say that it's acidic, low acidity, produces H+. You can say any of those. Then they ask for the equation. Give the equation to show the reaction of SO2 with water. So we have SO2 plus H2O, and we want to make something acidic. This one's really simple, to be honest. All you have to do is just add them up together. When you have an acidic covalent compound reacting with water, just merge them together. So here you have 2 hydrogens, 1 sulfur, and 3 oxygens. And that's it. That's your equation. Again, this is the AQA A-level paper 3 chemistry. Hi, for A-level, should I do past papers until 2016 or old spec ones too? Yeah, you can put it to old spec as well. You can do old spec as well, I meant. Why did you merge them? So I merged them because that's one of the rules that we have. So if you have any covalently bonded compounds, like this one, SO2 is covalently bonded, reacting with water, they will always just merge. It's a trick that you can use basically. How do we know SO2 is an acidic covalent compound? All covalent compounds are acidic. Are you able to record these lives? I believe they should be already recorded. Bond angles are so hard. I know what you mean. Hopefully we'll see some there we go. Next one's bond angles. Okay. So the next one's asking us, draw a diagram to show the shape of a molecule of water. Include any lone pairs of electrons. State the HOH bond angle. Explain the shape and bond angle. Okay. So I'm going to go a little bit in depth about this one because I want you guys to kind of understand how you can get the bond angle in the way that I do it, because somehow it's a lot easier, I believe, but it's up to you if it's easy or not. Yes, the answer is 104.5. That's right. So let's take a look at some bond angles quickly. I have what is called. So basically, what you need to look for is the 4 bonds. For example, methane. I should probably do this in 3D, but just imagine that I did do it in 3D. Methane, if anyone remembers, has the shape of tetrahedral. So with tetrahedral, we have the angle of 109.5 degrees. I want you guys to base it off of this one, rules of 4 basically. Base it off 4 single bonds like this. Then that means if you have ammonia, again, imagine it's 3D. Ammonia has a lone pair at the top. How do we know that? We can actually draw the ammonia if you want. So NHHH, single bonds with hydrogen. Ammonia is in group 5, so it has 2 extra pairs there, 2 extra electrons. And that's your lone pair. You can see here that it still has 4 bonds, but one of the bonds is a lone pair. So again, bond 1, bond 2, bond 3, bond 4. Once again, 4 bonds. So, once again, we're using the rules of 4. 4 meaning 4 bonds. We're going to base it all off the tetrahedral methane here. Anything that has single bonds, 4 single bonds, will be tetrahedral with a bond angle of 109.5. So I want you to base it off of this. Basically, just memorize that one, and then the rest of them will follow through. So the next one that we have, again, is the ammonia. Why do they have 2 lone pairs? You can draw the dot cross and see that there is a lone pair there. That means you have 1, 2, 3, 4 bonds, but the last bond is a lone pair. This one is what you need to know. each lone pair is minus 2.5 degrees. So we have one lone pair here, which means your bond angle will be 109.5 minus 2.5. And that gives you 107 degrees. That's how you know that you have the angle of 107 degrees. You can see here that I didn't even memorize that. All I did was just memorize that one, and I went through, follow along with the rest. The shape for this one is trigonal, pyramidal, or you can just say pyramidal. Kind of looks like a pyramid, so you can just think of it that way. And then, now we'll go to water. Water has two lone pairs, over here and over here. Again, I can prove that using the actual dot cross. There's single bonds here, so that's a dot and a cross, but oxygen is in group 6, so you're left with 4 other electrons. That's the first lone pair, that's the second lone pair. So you have 2 lone pairs. Once again, 4 bonds. 1, 2, 3, 4. So we'll base it off of this one again. That means your bond angle will be 109.5 minus 2.5 minus 2.5. This is for lone pair number 1, lone pair number 2. And you get 104.5. That's it. It's super simple. So you can base it off of the rules of 4 here. Now, this doesn't apply to the octahedral ones, but those are pretty simple. You only have like 2 of them that are octahedral and trigonal. What was the other one? Trigonal bipyramidal. So you can just memorize those ones. But the rest of these, you can see it like that. And so we have the shape. What are we looking for here? Yeah, so we have H, O, H, 2 lone pairs, bond angle 104.5 degrees. Now the explanation, it's always the same as well. So you can just say there are 2 lone pairs, lone pair, lone pair, repels more than bonding pairs, so decreases angle by 2.5 degrees for each lone pair. That's the explanation for it. What this means is that when you have 2 electrons next to each other like this, it will push it off to the sides. And what it pushes is the hydrogens. And that's why your angle is smaller. That's how we do the bond angles. This is the AQA exam board. I believe this is recorded, yes. I'll try and figure out how I can download it. You guys can screenshot this if you want. Yes, I will be doing the lives daily over Easter break. You can comment in my videos as to what exam board, what paper you want to do. I just got a lot of requests for AQA A-level paper 3 basically. I'm not sure where I can upload them, but I'll figure it out and then I'll let you know. What time do you do the lives? I do the lives. People have been asking me to do it above 10 a.m. So I'll be doing it around this time every day or so. I'll be doing some in the weekends as well. Oh my god, you really should sleep. We'll do some more lives, but yes, let's go into the 6th marker now. Okay, so let's see how we can approach a 6 marker question here. So the initial rate of reaction between sodium thiosulfate, I'm going to underline that because I believe it is something important, or I'm just going to highlight it so you guys can see that I'm actually highlighting it. Sodium thiosulfate and hydrochloric acid can be monitored by measuring the time taken. So we already told what we're doing here. Measuring the time taken for a fixed amount of sulfur to be produced. Describe an experiment to investigate the effective temperature on the initial rate of reaction. Include a brief outline of your method, how you will measure the time taken for a fixed amount of sulfur to be formed, how you will present your results in a graphical form. A sketch of the graph that you would expect. Okay, so let's have a look at that. Gas syringe, not... for other things, yes, but not for this one, and I'll show you why. Which subjects do you do? Is it just Chem? I do sciences and maths for both A-level and GCSE. Yes, my battery is 20. I will charge it later. Don't worry, my iPad lasts quite a while. Okay, so let's take a look at what we need so far. I'm just going to scroll up and show you why we are not using gas syringe. It says that we're measuring the amount of sulfur to be produced. And we saw here that sulfur is a solid. So we are using the disappearing cross experiment. You guys are right. The thing with the beaker. That's right. So I'm going to write that down there. We are going to use disappearing cross. And again, we knew that because sulfur is formed as a solid. So when you form a solid, you use the disappearing cross. You can use that, or you can use like masses, but it doesn't look like they want us to do that here. So we'll use the disappearing cross. If they produce gases, then you can use gas syringe or inverted measuring cylinder. Either one of them is fine. Okay, so let's do this. We're going to do a brief outline of what we want to do. So, there are 3 levels to answer this question. Level 3 would give you all 6 marks, so 5 to 6 marks. Level 0 is where you don't answer at all, or you just answer something completely off, so you lose all the marks basically. So let's do it in steps. The first thing we're going to do is talk about the method. After that, we're going to talk about the measurement. Then lastly, we're going to use the results. So, a brief outline of your method. The first thing we're going to do is say that we are using the disappearing cross method, but we can describe it instead of actually saying it. So we can do to a conical flask or beaker, up to you which one you want to use. It's always better to use a conical flask. Add 25 cm cube of hydrochloric acid. "25 centimeters cube" is a common value that we use. For volume, it's 25 cm cube, 10 centimeters cube, 250 centimeters cube. That's quite common as well. For masses, we usually say 5 grams. It's usually things like that. So to a conical flask, add 25 centimeters cube of hydrochloric acid underneath the flask. Put a cross on a paper. And then we will have add the, you can specify the volume or not, it's up to you. So you can say 25 cm cube to the flask. Start timing. We need to time using a stopwatch, so using a stopwatch. Why did I say that? Because it asks here how you will measure the time taken. So you can start timing using a stopwatch. Stop timing when cross disappears. Now, let's see what is being changed here. We know it's a fixed amount of sulfur, and we are looking at the effective temperature. So that means you're changing the temperature. So that's the independent variable here. So then you can say repeat at different temperatures. Record time t for cross to disappear. Ensure the same person is doing the experiment. Why do you think I added that last one there? Why do we want to say ensure the same person is doing the experiment? To make sure and improve accuracy. If you have a different person, exactly, less human error, more reliable, reaction time's different, that's the perfect one. So if you have a different person doing it, for example, if I were doing it and then my boyfriend's doing it, he has pretty bad eyesight. So he's going to say the cross disappears almost immediately, but I would still be able to see the cross there. So it's to prevent bias, basically. Different people would have different answers. Exactly, it's very subjective. That's right. So ensure the same person is doing the experiment. Repeat at different temperatures. I think I saw someone ask, do we do it at different intervals? You don't have to, because we're already using a fixed amount of sulfur. So we just want to see the start and the stop, but at different temperatures. If you are looking at gas syringe and measuring cylinder, then yes, you have to say that you are doing it at different intervals. That's right. So ensure the same person is doing the experiment. Use same volume and concentration of reactants, again, to improve the reliability. And then the last step is to talk about the use of results. So rate, let me put this on the side. Rate is always 1 over the time. So you can then plot a graph of the rate, which is 1 over time, alongside the temperature. What do you guys think? Will it increase the rate of reaction or will it decrease? If we increase the temperature, do we increase the rate of reaction? That's right. That's right. If you increase the temperature, you will increase the rate of reaction. But remember, your graph here is 1 over t, so it's not a straight line. That's wrong. A straight line is only for when this is t, not 1 over t. When it's 1 over t, you get a curve. Like this. It's not inversely proportional. If it's inversely proportional, that means that you will have a decrease in rate instead. So if it's inversely proportional, it would look like this, which is wrong. So that's your 6 marker. That's all you have to say. Why is it 1 over t? Rate is always 1 over t. That's a rule. And you can use this in both biology and physics as well. Rate is always 1 over t. Why don't we get a straight line? Because you have 1 over t here. You can try it if you want. So if you have y equals 1 over x, which is the same thing as saying y equals 1 over t. Let's say we put some values x, y, minus 1, 0, 1. Technically, we can't do minus 1, but I'll leave that there. So 1 divided by minus 1 is minus 1. 1 divided by 0 is infinity, so we're going to put nothing there. 1 divided by 1 is 1. I'm going to add some more. So that will be 0 0.5, 0 0.333. Oh, well, my battery is not lasting as long as I thought it would. So we have here the time would decrease. So increasing with time, the y value will decrease. But that's not what we're looking for, is it? So we're looking at it in terms of temperature. So this one, you can see, you'll form a curve. I'm just going to prove that it will be a curve first. This is if we have y, not that, then you'll get a curve like this, never touching 0. Now, the next thing that we know is that we're looking at 1 over time against temperature. And we know that increases, so it's a curve upwards. Yes, if this was for gas syringe, we'll record at different intervals of what? For this one, we'll do, for different intervals of time. So you do it for like 10 seconds. So measure the gas every 10 seconds. That's what you can say. Okay, but yeah, that's your 6 marker answer there. How do you know what goes on the x-axis? It's always the independent variable. And we said there that the independent is what we're changing, which is the effective temperature. So we're changing temperature, so temperature is going to the x-axis. The y-axis is what you're measuring. Okay. Draw the displayed formula of a molecule of H2SO4. Okay, so this one's interesting. You can either memorize this or try and understand it, but since it's just 1 mark, I suggest you just memorize it. But basically, sulfur is in group 6, so it will have a pretty interesting structure. It looks like that. You need this for the topic of acids and bases, but also for the topic of organic chemistry. It's not really common for organic chemistry, but you will also need it. Yeah, it looks like a butterfly. That's right. In aqueous solution, sulfuric acid acts as a strong acid. The sulfuric acid dissociates to form hydrogen sulfate ions and H plus ions. The HSO4 minus ions acts as a weak acid and dissociate to form SO4 2 minus ions and H plus. So they've already given you the equation here. You just have to write it down and balance it. That's the best thing about this. Give an equation to show each stage in the dissociation of sulfuric acid in the aqueous solution. So we know, firstly, we have H2SO4, which dissociates to form HSO4 minus, that's what it says there, and H plus ions, that's what it says there. And then the HSO4 minus acts as a weak acid and dissociates, that's the keyword, dissociates, to form SO4 2 minus and H plus ions. Simple, isn't it? You're just using literally what they said and translating it. Yes, dissociation should be reversible. That's right. The first one is the first one you can keep as forward reaction because this one's not reversible. Only this one is reversible. A student is required to make 250 centimeters cube of an aqueous solution that contains an accurately measured mass of sodium hydrogen sulfate. Describe the method that the student should use to make the solution. There's a clue here. That's the 250 centimeter cube. We want to know that we're using an accurately measured mass. These two things are keywords that tell you you're using a volumetric flask. That's the keyword. You're using a volumetric flask for this one. You can call it a graduated flask, volumetric flask, both of them are the same thing. So first thing you want to do is to weigh the solid using a digital balance. Keyword digital because it's more accurate. And then you can say add to the volumetric flask with a funnel to prevent spilling. Dissolve in water, preferably distilled water. I'm gonna have to go very soon, guys, but we'll do some more tomorrow. So, dissolve in distilled water, preferably. And then I think I'm missing something. Let me just read what I wrote. Add to the volumetric flask with a funnel to prevent spilling. I'm forgetting one step. Add to a beaker first, or flask. You want it to dissolve already before it goes into the volumetric flask. So then you can dissolve in water, add to the volumetric flask, and then add distilled water to the 250 cm cube mark. Invert and shake. What's the word? To ensure mixing. That's what you can say for a 4 marker. If it's a 6 marker, then you can go a little bit more in depth. You can then talk about weighing the solid a little bit more in depth. So you can use the, I forgot what it's called, kind of like the boat thing, or you can use a crucible. So you can measure the mass and measure the crucible first, add the mass, measure the mass with the crucible, and then after you get rid of it, measure the crucible again, and then see the changes in masses. Yeah, weighing boat, that one. Yes, my iPad is gonna die. We're gonna do more videos tomorrow. Oh my god, it's 2%. Yeah, okay. So we'll do more videos tomorrow. Hopefully this makes sense so far. Again, if it's a 6 marker, you can go more in depth about the top part, how you can measure the mass. But for 4 markers, this is enough. I am gonna charge my iPad because I do need to do my coursework after this. Is it at the same time? Tomorrow's Wednesday. I might be doing it a little bit more earlier or a little bit later. And yeah, make a YouTube and post these there. Yeah, I could do that. Are you able to make a video? Practical methods we need to memorize. Yeah, sure, I could do that. If you guys have any requests, put it into the comments of my last video, I think. And if any of you guys are looking to go into university or looking to apply to university but don't know how, look at Crimson Education, look at my video on that. They give you a free consultation about how you can get into your dream university, and students from Crimson Education are 7 times more likely to get into their dream university as well, both in the USA and in the UK. Okay. Thank you all. A-level tomorrow. Yes, we'll continue with this paper tomorrow. And after that, we'll do biology or physics or maths or GCSE, anything that you want, you can let me know. Yes, we are doing chemistry tomorrow. No problem. I'll see you guys tomorrow. Thank